Hello, everyone, and welcome to episode number 77 of the Hyperthesis podcast. We have a very chill but cool episode today, and we are excited to start. So, hi, I'm Patrick.
I'm Feely.
And I'm Leah.
Okay.
Bow, 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 bow. Oh, sorry. I had too much sugar this morning.
Oh boy. Well,
No, leave it in. Just leave it in.
okay, ready?
Yeah. I was born
Well,
ready.
if you haven't been paying attention to our Instagram page, you may not have seen that we actually met up in person for a certain celestial event. So we are fresh out of meeting up. We are still recording to you from 3 unknown locations in Canada, but just know that we do actually see each other. This time for the first time, I think, in like 4 years, but we still do see each other occasionally. So, today, as you might be able to tell, will be a bit more of a chill episode. We haven't had too much time to prepare things and just want to kind of reflect on what happened over the weekend, especially on Monday. And then there's also a couple interesting things that have come from the news, which we'll focus on for intertopics in our story. So as our intertopic, does anyone have anything they would like to discuss?
Yes, so this is a fast and loose topic that I found out. I think I talked to one of the physicists, and it came up because, I'm a statistical physics kind of guy now. I think I've changed, right? But when I think about early universe or like particle physics and dark matter, dark energy stuff, there aren't many, to my knowledge, like stat mech involved. You probably can do it, right? But I can't really think off the top of my head, like, oh, what are phenomena that's like statistically found or well thought about too much. But I heard about this space-time bubbling event in the early universe, which is they postulate or they assume or they hypothesize that there is a phase transition happen in the early universe that could account for the matter-antimatter asymmetry or some type of, or how it becomes to where the universe is now. So I think if you think of early universe like very early as very homogeneous, because maybe the Big Bang happened and there are stuff that comes out, and you could imagine things to be pretty homogeneous, right? Be uniform. So how does things come about to be stars and stuff later? And if I read it correctly, the space time kind of form this has some fluctuation instead of just staying still. So everything fluctuates, but if the fluctuation is large enough, it kind of form kind of bubble. So imagine if you have a boiling water in a pot, right? Because you have enough energy, so the molecules move fast enough or have enough heat, quote unquote, in the space-time equivalent. It could be different, right? But imagine it's kind of have enough heat to fluctuate, and it's gonna boil per se, and it could form this space-time bubble. And then if it happens often enough, it's gonna basically nucleate a new phase and just propagate throughout the universe. And apparently those events, those bubble is gonna form and pop, and it will create, instead of sound, popping sound, is going to create a gravitational waves instead. And we should be able to detect it, but not right now. So it's gonna be some kind of like popping noise, but it's gonna happen a lot. So it might be some kind of white noise that we can detect gravitationally. But the thing we have to use to detect is gonna be not the LIGO or what we have now for gravitational wave, but it has to be better. So it's going to be the laser interferometer space antenna, which is basically the LIGO in space. They call it the LISA or LISA. And the provisional launch date is in 2037. So it's not that long, not that long, but in terms of human life, that's kind of a little far. So they try to detect this early universe phase transitions. And with the resolution of the LISA, we should be able to find it. And now the question is, well, if you find it, does it really mean that that's the event, or maybe it's coming from somewhere else or something else that caused it? Or if we don't find it, do we have to? How much of the theory do we have to amend to support the evidence? So, and basically, a lot of these are, I think, are kind of beyond the standard model with the dark matter and such now. So I'm not sure where it's gonna go.
So just a quick word on Lisa. It's a very interesting project. And again, you said it's still, well over a decade before it's actually launched and put into place. But I just want to draw a couple comparisons with Lisa and LIGO. So LIGO has two facilities here on Earth, both in the United States of America. And they consist of these cavities that are very still. They have to be very still and vibration insensitive and all of this. But essentially what they're able to do is reflect light back and forth in these what are known as Fabry-Perot cavities. For anyone that's taken a lasers course, you will know what those are. But essentially it takes 4 kilometers lengths that are at right angles to each other. And then based on reflection, is able to extend that to 1,200 kilometers of path for light to travel. And so having a longer path means that you're able to detect these more sensitive gravitational waves based on the shrinking and expanding of space-time. So that's for LIGO. For LISA, since it's going to be in space, we aren't limited by something that we can put on the ground. And so LISA will be an equilateral triangle, so just 3 points with 3 devices at each corner. And the actual length of each side of that equilateral triangle will be 2.5 million kilometers long. And it will be flying along kind of an Earth-like heliocentric orbit, so it's going to orbit the sun separate from the Earth at about 1 AU, so close enough to Earth that it's kind of in the similar range and similar orbital period, and that we can get signals from it. But this thing's going to be massive in terms of its span. The sensors themselves will not be 2.5 million kilometers long, but the light will be able to travel so much further, allowing us for incredible sensitivity for monitoring these kind of gravitational things.
Yeah, I actually really like the terms they use too. Like they call it in early universe they call it the primordial plasma. Like maybe it's just because there are charged particles just floating around, and if it's cooling down, it's gonna be some kind of phase transition, right? And or if it's heating up, it's gonna be some kind of, hopefully. I mean, phase transition is a very specific phenomenon. So it doesn't happen all the time. Even if it's heating up or cooling down, it has to hit certain criteria, right? And so it's gonna be interesting to see if they can find this kind of bubbling event. And I wonder, there are probably people who are modeling it using statistical mechanics and quantum field theory to try to figure this out, how much they should expect in terms of the amplitude and maybe duration, or how much gravitational wave should you expect, and or even how long it is. I'm not sure at all. So maybe one day we get someone who knows what they're talking about. But the launch is gonna be 2037, and it's gonna be so far away. We got some time to do some connections and research about it.
Okay, well, very interesting stuff, and certainly an exciting project coming up. I'm just looking at a very cool animation of how it orbits. So essentially, the 3 different sensors for Lisa will be in 3 separate orbits that are at different inclinations to the sun and at different areas. So we'll always form a triangle, but it's actually 3 separate orbits kind of orbiting behind the Earth. So it will be in the same orbit as the Earth, but kind of orbiting around one of, I believe, the Lagrange points, it looks like. Super cool project. Very excited to see when that happens. And again, it's going to be very, very powerful once it comes online. So, if there's no further introductory topics, we'll move on to our main topic, which, again, this is more of a relaxed episode. So, we will just kind of give you an update on what's going on in our lives and why we were all together in Hamilton recently / Toronto.
There's a big difference there.
Yes, yes.
As I found out, about a 2-hour commute by transit.
Yep.
But as some of you may know, or as some of you may have experienced, we had a solar eclipse in North America, the second one in 7 years, and the last one for the next 20 years. But I was able to fly down to Ontario and join Feely and Liam. We met up in Toronto, and then we were all able to experience the eclipse separately. I was with Liam, and then Feely was in Kingston. But luckily, Hamilton and Kingston were all along the path of the eclipse. So we all got to experience the totality of the moon blocking the sun. And for more information on the eclipse, you can listen to last week's episode.
We got 1 minute more of totality, by the way.
Did you really?
Oh, yeah. I think you guys got 2. I think we got 3.
Yeah, we had like 2:10 or something like that.
Yeah, we got around 3 minutes.
Yeah. So for those of you listening that you're not familiar with the eclipse, there is a path of totality that's just several tens of kilometers wide, and it depends, again, with the alignment of the celestial bodies that we talked about last week, just how wide that path is, and also where on the Earth you are. And so this path of totality happened to go through southern Ontario, and kind of its center, at least in southern Ontario, close to Hamilton, was in Buffalo, and then that moved up through Montreal, and then New Brunswick and Newfoundland, and even hit a very top corner of Nova Scotia. And so, depending on where you are within this path of totality, where the sun is 100% covered, the amount of time that you have in which the sun is covered changes depending on how far you are from the middle of the path. And this is because if you think about it, the moon and the sun are spherical objects, or circular objects when you look at them in the sky. But depending on where you are in the path, then the moon will be kind of shifted one way or another.
Well, basically, it's the moon casting shadows on the Earth, right? So the middle shadow is gonna have the longest time of totality. And I was lucky to be in somewhat close to the middle, right? So I got 3 minutes. And, if I flew in for a 2-minute event, that's a commitment. And there are people who commit more, the eclipse chasers around the world who just go see eclipse. And I think the next time it's going to happen in Kingston, I think for me, it's like 700 years later. And, the last time it happened in Kingston 700 years ago. The next time is in 2399, if I remember correctly, for totality.
The other thing is that, as always, you're at the mercy of the weather. So when me and Patrick and some of our friends were waiting for the eclipse, there was all these clouds everywhere, and we were just like praying that they moved in time for us to see it, which they did. Very, very luckily. It was almost perfect timing. There was clouds, and kind of right as totality was approaching, they just shifted.
It's not luck, actually. I talked to an astronomer, and it's like, no, it's called inversion.
Yeah,
So
but
because
there's also some chance to. I mean, all of Niagara Falls didn't
yeah,
really get to see it at all because of the
yeah,
clouds.
yeah, but close to totality because there's a gradient in temperature. The temperature drops, right, and that create this temperature gradient, which create convection, which push the clouds away from the path of totality. So that is pretty cool effect. So
Yes.
apparently it's to become more clear.
It was certainly interesting, though, seeing the weather effects of the eclipse because we missed the first contact point. Just an eclipse will have 4 different contacts. So when the moon first interacts with the edge of the sun, then when the other edge of the moon is essentially covering the sun, that's when you have your total eclipse. Third contact is when the next edge of the moon touches the sun, and then finally when the moon completely clears the sun in the sky. So we missed first contact, and then since it was cloudy, don't do this, but you could actually see the eclipse with your naked eye without the need for eclipse glasses, just because it was so cloudy. So little light was getting through that you could actually, essentially, the sun was and the moon were casting its shadow on the clouds, and then you could see it that in the clouds. But then, of course, it cleared up, and you could actually see the blue sky moving towards us from what I think was at the actual direction that the moon was moving, or at least the moon shadow is moving over the Earth.
Yeah, the totality is such a, to me, it was incredible because from 99 to 100%, and that point from 98, 99 to 100%, there's like this big difference. Because like at 98 and 99%, the sky is still, lit up, right? And I remember I was looking at the sun and the moon, of course. And with the glasses on, I see when it's like um only have the slither left. I'm like, okay, it's still a little bright. And then when it hits totality, when I see the last bit of the sun get gobbled up, and I took my glasses off, like, oh my god, the horizon just transitioned from like blue sky to this kind of dusk slash dawn vibe. Because I was at the pier by the lake, so I can see the water, the people in the kayak, in the lake and boats. That must be amazing. And the reflection from the water, and look left, look right, look up. It's such a beautiful thing. And I didn't expect the halo effect that prominent, because when you wear eclipse glasses, everything else black, and you can see the sun as like the orange circle, right? And when you take glasses off at totality, because you can do that at totality, you basically see the rays from the sun, but not the sun itself. It's kind of like, some people I think describe it to me as like watching Interstellar's black hole kind of imagery, where it's like dark in the middle and there's like this halo of light around it. And it was, I just, what do you call it? Sublime. It was really overwhelming feeling. And then you start looking at the feature of it. You can see a little red dots around it, especially at the bottom of it. I think that's the corona. The sun spits out gas and plasma and such, right? So you can actually see it. And I think they use a lot of it to confirm confirm the Einstein theory of relativity too. But that 3 minutes was wonderful. So how about you guys? How about Liam?
Yeah, it was really cool. It was, I don't know, it was just kind of wild. Like, it got so cold too, and it went from being like, I don't know, 15 degrees out to like cold enough I could see my breath in the kind of time that the sun was not fully covered, but like mostly covered. I remember that was in 2017. We talked about this in the last episode, but there was like a partial eclipse in Nova Scotia, and we were all there to experience that. And it wasn't as cool because there wasn't totality, and you didn't get to see the big black ball in the sky and how dark it got. But I noticed the temperature dropped a lot, so I was very kind of like conscious of that during this one. I was every few seconds I was like, "Ooh, it's getting a little colder." Um, so I thought that was kind of cool.
Yeah, maybe the dark sun is I never seen totality, right? So I never seen the sun dark, like the black sun. Basically, it reminds me of Ingrid Malmsteen's song, but it's. I, I'm glad it was packed though. I mean, there's a lot of people there because like I would say a little early. I want to see the entire eclipse, but like when it's like 15 minutes out from totality, like the pier just filled with people.
Yeah, me and Patrick and our friends, we did it in this little park kind of near where I live. So it was pretty nice because it was pretty open and there wasn't too many people around. There was some people, like a good amount of people came to this random park, but it wasn't packed or anything. It was very nice, and yeah, it was very cool to kind of like, I don't know, it just makes you appreciate how small you are. At least that's how the feeling I get out of it. It humbles you. It reminds you that we're just on this little ball in the universe.
Yeah, that's the sublimity, right? Well, in art, I think some people would say that overwhelming feeling because this is distinct from beauty. But let's let's not go there.
Well, I was gonna say that it was also a good weekend because the three of us went to Toronto, which is pretty nice. And I think it was the first time we'd all been together in like 4 years or something. And Patrick revealed to us his very nice T-shirt about the Hyperthesis podcast, which is very cool.
Yes, shout out to Paige for making that shirt for myself and a super fan of the podcast, Mr. Plow.
Mr. Plow is my favorite. Holy, love him.
I think, yeah, now that because you mentioned that we have seen it before, I think we've seen it before on the when we were recording. Yeah, but it was nice to see it in person. Yeah, so I made a little trek up to Toronto just for the day, basically, to see the guys. Yeah, it was good. We except for Liam, who has his arrogance, he wouldn't touch the CN Tower. It was a shame.
I've been to the CN Tower so many times. I don't need to go up and like touch it. I've eaten like hot dogs in front of it and stuff. I've been to the aquarium, Ripley's aquarium there. Like, one day I'll touch the CN Tower.
But both of us touch it, and you wouldn't do it.
I know, I have to give myself a reason to go back. I can't do everything all in one trip. Yeah, spread it out. But yeah, it was kind of fun. What did we do? We didn't do anything too exciting. We walked around, we got some food, we played pool.
Yeah, we walked a little bit. Like I remember, like I woke up next day, my legs were a little like a little tingly. I was like, did we walk that much? Oh, it's only 25,000 steps.
Not too bad. Not too bad. Patrick got a nice tripod for his camera, which we used during the eclipse. I'm excited. You gotta send those photos to us. I need some by tomorrow so I can post them to the Instagram for this episode.
You have one for sure.
I have one, but I need like a few more, or I need a little time lapse video or something. I need at least like 2 more, maybe.
I will see what I can do, but
no rush.
Yeah,
They don't need to be like the high quality, finalized ones. Just send me like.
Yeah, so just so for the entire eclipse, I at least for what was visible, I did a time lapse photos of the slow coverage of the sun and then the slow recession of the moon over the sun's face, along with a couple photos of the totality itself. So hopefully you'll see those on the Instagram. And if you're ever photographing the sun, make sure to use a solar filter. I would recommend a Mylar filter because it's the same material pretty much that's used for eclipse glasses. So you can actually look through your camera lens if you're photographing the sun. Whereas if you use something like a neutral density filter, it might not always be the best to look through the actual lens. Whereas Mylar filters are definitely safe. You get a little bit of color distortion, but still probably a safer bet, especially if you want to stare at an eclipse or just the sun.
Well, the ND filter is definitely not enough. And ND filters, they also have a different stops, right? Like different density. So if you have a really low density one, well, that's gonna be way not enough. Because if you look through Eclipse glasses, like it's pitch black. You can't see anything until you look at the sun. Then you see the circles. Like, wow! Because you can wear Eclipse glasses. You look at the light in your room, it's still pitch black.
Yeah. Just to know, if you do ever want to photograph the sun with an ND filter, make sure it's at least 16 and a half stops. I think like 16 is a minimum for sun photography, so you don't burn your camera out, because that light's focused on the shutter and it can actually melt the shutter. If you have that type of camera, if you have a mirrorless camera, don't do it either. But
yeah, the the sensor is gonna burn, right? It's like you're not supposed to put your camera at the sun. And like Liam said, like the temperature drop really shows how much energy the sun is giving to us. I mean, one could say like almost all energies we get on Earth is from the sun, right?
Yeah, I mean, most places it gets colder when it's nighttime because the sun's not shining on you. Or even when we were in Toronto, right? There's so many big buildings that there's a lot of shade. And when you're walking through these kind of like shady areas, it's way colder than when you're out on the waterfront in the sun. But it's kind of like, it's still, like you said, it's kind of mind blowing how it's just it's not like a very, I guess it's like, it was around 2 hours and a bit of the sun being partially to fully covered, and it makes a huge difference.
Yeah. The sun is like, even when it's cloudy, some people still get sunburns, which really fascinated me. Like, it's cloudy as heck.
Well, I mean, I get sunburned when I ski sometimes. Like, it's turns out I'm pretty white.
so going back to the eclipse, one thing that I want to mention, actually a couple things, but the first thing I want to mention is the fact that it seemed to take so long for totality to happen. So the moon is moving across the face of the sun in the sky and slowly casting its shadow. But what I noticed is that there was just this tiny sliver for the longest time. Now, whether that was just excitement for the totality and time seeming to move slower, but it seemed like a good 15 minutes that thinking, oh yeah, it's going to happen right now. It's going to happen right now. But the sliver, like, just got gradually smaller. Whereas beforehand, it seemed to be moving quite quickly across the sky. So there was this kind of anticipation of, oh, when is it going to happen? When is it going to happen? And we even knew the exact time that the moon would cover the sun to within a couple seconds. But even then, it just seemed to take so long once that final portion, like the 99.5% coverage, goes to 100%. It just seemed to take so long.
I was thinking right before the eclipse starts, like, whoa, what if it doesn't happen? Maybe everything I know about science could be just wrong, and I might just change career. Like, all right, someone messed up. Is not today or something like that. They'd be like, or maybe physics, it's just simply wrong. But I'm glad it happened, right? I'm glad things come according to the calculations, and it's like, whew, what a relief.
What's that thing they say that, like, a theory's a theory and you can have 10,000, 1 million pieces of evidence to support it, but the moment you find like one counterexample, something's wrong with your theory. And I'm talking about like legit counterexamples, not like weird conspiracy theory stuff. Talking about like actual ones.
Well, we just go on particle data group, all right? Look for violations, and you might start to doubt the standard model.
Standard model is Swiss cheese.
Yeah, I mean, I think it's the best we have right now, and I think, well, it's not it's not a complete description of reality, right? But even though we have a lot of violations that happen all the time, these colliders, it's still pretty good description of reality until you try to explain like maybe some things about like early universe, something would happen there, maybe those type of violations need to happen to create this matter antimatter asymmetry. Like it's the world we live in or the universe we live in is kind of strange in a sense when you do science. You're like, well, you expect things to be symmetric and beautiful mathematically, or they are beautiful mathematically, but they're not as symmetric or as nice in a sense. Maybe I'm wrong. Maybe everything is symmetric and nice. We're just in the long term fluctuation of a state that will turn back to its opposite state, and overall over trillions of years might look very smooth. Who knows, right? It's a matter of scale. The human perception of scale is very limited, and I think the eclipse kind of showed us part of it, right? It's like that. Wow, this event, this eclipse event, has happened all the time in a universal sense, right? 18 months for each one is like very short. So, but like we stare at the sun for 3 minutes during totality, 2 for you guys, and we get to experience this. Could be life changing to some people. Maybe if you're a child, want to be a scientist, might change your life, right? But in terms of the universal time scale, that's very like minuscule, infinitesimal.
Maybe if you're a bunch of Greeks and Romans in a war.
Exactly. Right. So it's really put things into perspective in a sense where, well, this event for me is probably the best natural phenomenon I ever seen in my life. I was trying to think about something else, like, well, what have I seen? Because I've seen like those artificial ones before when you do lab tours, what we've built as mankind. You see the Cherenkov radiation from the reactor. Like, well, this little glow is pretty cool, but that's like just a glow. Um, um, at the time was like really cool, but look, right now I'm just like, whatever. Maybe I'm just so desensitized to physics phenomena that's just nothing even came close to the totality of the eclipse. I would say is even the lunar eclipse is a little bit boring. It's just a little red moon.
Yeah, I agree with you though. I really like the natural phenomenon way more. I think that's way more interesting to me than like, I mean, it's all interesting, but I don't know. Like my hobby is photographing these rainbows and ice halos because something about the fact that they just appear without people needing to make them appear like I find that very cool. So there's some pretty stunning ice halos you can see, which I would argue rival totality.
Well, because to me totality connects us into later in a cosmic sense, right? Because like halo and whatnot, like ice rainbows, they are weather effects. They're something that happen on Earth. Well, probably somewhere else in the universe, but totality or like eclipse is the effect from our solar system, the Newtonian gravity, and is the scale of its conception is larger. So instead of looking at some molecules do this, instead of some molecules do that, no, these are very large objects that cast shadows. The principle is really simple. You don't have to do quantum mechanics or any complicated things to figure out the eclipse, right? It's just classical mechanics. Well, it's not that simple of calculation, but one could imitate that with like a ball, right? 2 balls, actually 3 balls, and it's like, oh well, and a light source. It's like, well, this what happened. You can demonstrate it on Earth easily. And then you realize like, well, it happened in the more of a solar system scale, and we know that it happened in a cosmic scale too. Well, people get eclipses. If you're on Mars, you get eclipses. You get bunch of if you have a moon, right? And I think it connects us to a much larger sense of self. It's like going to a Grand Canyon, seeing that. But that's also like I think as scientists, we see the world not in the moment that we are, but in the history too. If you look at the Grand Canyon, for example, it's like, well, what do people see? Maybe you see a little bunch of rocks and stones and such. But that's why they say to see a world in a grain of sand, right? William Blake. But you can, if a geologist, you could see, oh, maybe there were glaciers here. Maybe these are the water erosion instead of just bunch of rocks. And when you look at geographical features of a lot of places, you can basically deduce that, oh, well, what caused it, and it could lead to a larger description of a whole history of Earth. And I think the eclipse leads to this description. Maybe it's just I'm reaching here, but of the solar system, right? Because eclipse, instead of just one time thing, is something that we can extrapolate to something that happens all the time, and this is the natural feature of being on a planet with the moon, or maybe a planet with the outer celestial object that's in the way of your light source, or the star that in the middle of your system. In our case, it's the sun, but to me, it really provides perspective of the theory that one of the most simplest theory you learn in physics, right? Or one of the first theory you learn in physics, which is Newtonian stuff, which is equations of motion, the motion of objects. And I don't know. It's hard to explain because to me, nothing ever came close to it. Maybe I haven't explored the world enough, but I don't think anything would come close to this obstructing the sun that we see every day. Because I love the sun. I love sunlight and being outside, have the sun on my skin. It just feels good. Some people say like, why you like the heat and a strong humidity? I would say really humid and hot is great because it feels like the earth is hugging you, and so
Sounds like something someone from Thailand would say.
a lot
I
of people wouldn't say that either. People just like to be in the shade and not get burned by the sun.
that's me. I like being a basement dweller.
So, just kind of going back to the eclipse and thinking about it, and just thinking even more about your personal experience with it. Are there any kind of takeaways that you'd like to share? Things that people can prepare for if they're tracking solar eclipses, or what a solar eclipse is coming to their area, or something that would motivate people to go see a total solar eclipse?
Maybe this isn't quite what you were asking for, but have you seen those posts talking about how immediately after the eclipse, one of them, like the Google searches for "why do my eyes hurt" skyrocketed. So my take-home message from the eclipse is that common sense needs they need like a course on common sense in school or something. I don't know, because like if you stare at the sun and it hurts your eyes, you should probably stop. Or this eclipse is coming, and I guess maybe it's people aren't connected to social media enough. Maybe they didn't know that like even the tiniest sliver of sunlight passing around the moon can blind you if you're not careful, and they stared at totality too long. I don't know. I feel like again, we're in the physics community and the science community, so this is all stuff that like we hear all the time and have a lot of knowledge on, but I don't know what like non-scientists, what their view of it is.
Well, I wouldn't say the not stare at the sun is a science thing. It's just I think it's a very normal human thing.
No,
yeah,
but
thousands of years ago. Yeah,
but I think what some people might not know is that like how you can look at the eclipse during totality safely, but the moment it's not totality, even like that 1% of sun leaking over the edge is enough to cause eye damage, and it could be that people don't realize that. I don't know.
yeah. I mean the intensity calculation, you can calculate it, right? Like
It's a lot.
because that's exactly. For 1%, 100% is just 2 order of magnitude. It's not that much.
Yeah, even 1% of staring at the sun, like staring at 1% of the sun is quite enough to hurt you, especially when your eyes have been all dilated and it's been dark out for a minute or
Yeah.
something. And
You could think of similar to sound, right? Like because decibel, bell unit is a logarithmic unit, right? So an order of magnitude doesn't even change it that much, right? It's like it's only changed by like very little, like 1 or 2. Is it 10 decibel per order of magnitude? Maybe around that.
I don't know.
Yeah. So
But
well, I mean,
anyway,
you multiply it by 10 is basically you add 1 to the logarithm, right? Is it? Yeah, and then
Yeah.
you
Yeah.
multiply by 10. Yeah, so it's like 10 decibel is like 10 times. So if 20 decibel is like 1%, right? Or like from 100% to 1%, you reduce by 20 decibel.
yeah, but I guess be careful with the sun is the take home message. Nature is powerful, and it can hurt you if you don't know what you're doing, and that goes for just more than staring at the sun, I guess. But anyway, yeah, I thought it was really cool. I'm very glad I got to see one because it's that you have to travel to see them more often than not. Patrick had to travel to see it, and luckily he didn't have to travel too far. And Feely, you and I just happened to be in the right place at the right time, so that was very fortunate. Most people only see like 1 or 2 of these in their life if they're really lucky. Like my dad, when he was in like primary school, there was a total eclipse over Nova Scotia, so he was a very young kid, and they got to like experience one. But my dad's in his like he's in his 60s now, and he's never seen another one since. Because if he wanted to, he could have traveled and saw one, but it's very rare that one just stumbles over your head. So I think I'm just very happy that I was in the right place at the right time.
Yeah, it makes me coming to Queens worth it now, this is the only reason.
Yeah. Oh, what did my girlfriend say? She said something like, "Finally, Hamilton's given us something in return."
It makes the years of subconsciously coaxing you to live in Southern Ontario worth it.
Yes, exactly. I mean, I could have just went to like New Brunswick to see it or something, but whatever.
Well, my take home message about the eclipse is, it's a once in a lifetime experience. And like Liam said, it usually doesn't stumble upon you that often. And if you have a chance to see it, go see it. And, I saw it with my friends, is good. But I think you should take some time to look at it and think about it internally by yourself. I'm on the opinion as that the best way to travel is alone because it leaves you with the thoughts in your mind and like, okay, what does this natural experience connects to me, and what thoughts got provoked. And it's like traveling to go see art and museums and you see history, and it's nice to talk to people about it, but it's actually great to have this internal conversation in yourself. And you look at Eclipse, what do you think? What goes on in your mind? How does it connect to what you know, your knowledge, your philosophy, your principles, and you as a human being? I think it could be just another Tuesday, or it could be a transcendental experience, right? So it just depends. So, but I always encourage people to look into yourself, find some profound meaning, or for something that might be meaningless. And I think that's the take-home message, I guess.
Very poetic. I was going to ask Patrick about, before we get to our story, I was going to ask Patrick about, he had a presentation, I think, yesterday. I was going to ask you, so you're going to Spain at some point, right?
Yes, I'll be leaving in 2 days.
Yeah, I just wanted to ask you to talk about that a little bit as a little update on Patrick's life.
Well, I will provide an update once I'm back.
Okay.
Because the presentation I did yesterday will be similar to the one I'm doing at an imaging workshop in Spain, and so this one focuses on like spectral imaging and orbital remote sensing. So a lot to do with my research. So I've gained some interesting results from some orbital satellites over tropical dry forests, but I'll talk more about that after the conference when I have a bit more to say about it. This was
Very
like a
good.
dry run.
That was the warm-up presentation.
Yeah, exactly.
Very good.
But yeah, just one final thing I want to say about the eclipse before we move on to the story is don't worry about getting the shot. So I had set up a camera, like got it all set up, and just set the auto timer, took the filter off when totality started, put it back on so I didn't fry my camera. But other than that, I wasn't really worried about the shot during totality. It's more important to, one, get into clear area where you can see well around you, especially that kind of 360-degree edge of the shadow. And it's also important to actually see it, like what Feely was saying. It can be a transcendental experience, and if you're futzing with a camera for the entire time, then you're missing that experience yourself. And you can see photos of it. Chances are someone took a better photo than you did. So don't worry too much about it.
Yeah, I think my view maybe comes from the more introverted point of view, right? It's just like, no, because a lot of people go see with their friends. I mean, I did too, but like, I just need that a couple minutes when it happened to just sit down in silence. I think the people I went with did similar things, right? Sit down in silence is more like, that's why people should doing a little bit of meditation, maybe not to find nirvana, but to slow down your thought a bit. Think about what happens. Think about things. Be introspective. Be retrospective sometimes. I think when every time I see natural phenomena that's really cool, I would just like, oh, like go see the great nature, right? And you want to sit down at the edge of the cliff, or not the edge of the cliff, or a very high space and look over the forest, the greenery, and maybe the ocean or the lake, and to just ponder, have internal dialogues. And that's my favorite thing to do, by the way. It's just to just have this long dialogue with myself. Is sound a little bit insane, but I think that's what a lot of people do. So I will leave it with this.
Well, go watch a solar eclipse if you have the chance, and it's worth the experience. But moving on, before we get to our story today, I'm going to tell you how you can reach us. So, as I said at the beginning of the episode, we have an Instagram account where you can see some cool pictures that were taken during the eclipse, along with our little Hyperthesis reunion. So you can go check that out. And you can also send us a DM on Instagram. So if you have questions, concerns, or if you want to be a guest on the show, you can send us a message over Instagram. If you don't have Instagram or don't want to send us a message there, we also have an email. We are hyperthesispodcast@gmail.com, where we check it pretty regularly. And again, if you have questions, comments, concerns, or if you want to be a guest on a show because you are an expert in your area, feel free to send us an email or a DM. If you're listening to us, congratulations, you found us. We are on most podcasting services, including Apple Podcast, Google Podcast, which is still working for some reason in Canada, but is also YouTube Music, Audible. We are based out of Spotify, but you can find us pretty much wherever you find your podcasts. If you are able to, give us a rating or a comment or a review on whatever podcasting service you use, or you can find us on YouTube. We are, if you just search the Hyperthesis Podcast, we'll pop up on YouTube, and you can see a mostly up-to-date episodes with some beautiful visualizations. This season is in black and white, which looks really nice, or grayscale, I should say. And you can also leave a like, a subscribe, and a comment on our YouTube channel. So however you find us, make sure to share us if you think your friends would be interested in this, or your enemies. And also make sure to reach out to us if you are interested in being a guest on our show.
I'll make sure to send this to all my enemies.
amazing. They can grind at the sound of your voice.
Excellent.
Anyway, moving on to today's story. Just recently, actually the day of the eclipse when we were all celebrating such a monumental occasion, we lost a very important and well-known physicist, Peter Higgs. So Peter Higgs was a very well-known physicist. If you are in physics, you know his name. And even if you aren't in physics, you know about his contributions of the Higgs boson and the corresponding Higgs mechanism and the Higgs field, which, of course, none of which he named after himself intentionally. It was other people that did that. But he passed away just earlier this week on April 8th at the age of 94. And to celebrate his life, I want to take us through a quick story about his life. So this is the life and times of Peter Higgs. So Peter Higgs was born on May 9th, 1929 in the Alswick district of Newcastle upon Tyne in England. His father, Thomas Higgs, and his mother, Gertrude Maud, were both raised him. And so Thomas Higgs worked as a sound engineer for the BBC, which meant that he needed to move around quite often. This combined with childhood asthma meant that Peter Higgs was unable to attend a lot of early schooling during his childhood. Now, for secondary school, he did move in with his mother Gertrude, who lived in Bristol at the time, and he attended the Cotham Grammar School for secondary education. Now, this was during World War II, so of course things were disrupted from time to time, but this is where Higgs actually started taking true interest in physics because he was inspired by an alumnus of the school, Paul Dirac. Now, after the war in 1946, Higgs moved to London, where he attended King's College, where he would eventually receive his first-class honors degree in physics in 1950. In 1952, he received his master's degree from King's College, and then he also did his PhD there, with a focus on molecular physics, with the thesis dissertation titled Some Problems in the Theory of Molecular Vibrations. So he didn't actually start out in particle physics or anything like that. He looked at molecules for his PhD. Now from there, Higgs moved around the UK quite a bit, going from the University of Edinburgh to the Imperial College of London and to the University College London. But he eventually returned to the University of Edinburgh in 1960 to take up the post as a lecturer at the Tate Institute of Mathematical Physics. There he stayed for the rest of his working career, eventually becoming the personal chair of theoretical physics in 1980. He then retired from the department and the university in 1996, becoming a professor emeritus. But he had quite a few accomplishments under his belt during and after that time. He did also marry another lecturer at the University of Edinburgh named Jodie Williamson, and they had 2 kids together, and they also have 2 grandchildren. But they did divorce in 1972, but remained friends until Williamson's death in 2008. Now, during his time at the University of Edinburgh, Higgs thought about mass, and he started to develop ideas that particles themselves are massless and actually get their mass from some sort of field, which we now know as the Higgs field, that permeates the whole universe. We've talked about fields before. I won't go too much into them, but essentially the Higgs field dictates what's known as the Higgs mechanism, which is the process in which particles are able to interact with the field and give some of the mass, while others don't really interact with that field, so they don't really have much mass, if any mass at all. Now, much like any other field, at least a quantum field, there are excitations that occur, which form a particle, and the excitations from the Higgs field form a massive no-spin boson, which in this case is known as the Higgs boson. And Feely made a fun comment before we started recording that the Higgs boson is the only elementary particle So we aren't talking about generalized particles or like more complex particles, but it's the only elementary particle that is named after a person. All the rest are kind of named after the Greek words or just different characteristics. Now, it's said that Higgs came up with the fundamentals for this mechanism and these fields after a failed camping trip in the Scottish Highlands, but there was no eureka moment for him. Instead, he produced one short paper that talked about a loophole in another theory, Goldstone's theorem, if you know it, and also based on work by Nobel laureate Yoshiro Nambu from the University of Chicago. Now, Higgs's second paper on this topic, and the original paper detailing the Higgs mechanism, was submitted and then rejected by physics letters because it had, quote, no obvious relevance to physics, unquote. He then added an additional paragraph and submitted it to Physical Review Letters, PRL, in which it was published in 1964. So this is the paper that also predicted the Higgs boson. And several other physicists at the time, which he cited in this paper, also had kind of similar ideas. These physicists include Robert Brout, Francois Englert, Gerald Guralnick, and C.R. Hagen, as well as Tom Kibble. And they had kind of all reached similar conclusions, and Higgs expanded on this work. And it's actually very interesting because this mechanism was actually first described in 1962 by Philip Anderson, but he didn't include a crucial relativistic model. So there was a lot of work going on at the time, and Higgs happened to have the paper that really kind of fundamentally changed everything. And his ideas were proven quite a number of years later, almost 50 years after the original publication, on July 4th, 2012, at CERN, where it was announced that the ATLAS and CMS detectors at the Large Hadron Collider had detected the presence of a new particle known as the Higgs boson. So its mass is around 126 giga-electron volts, and Higgs was very excited that it happened in his lifetime. As a funny irony, the confirmation of the Higgs boson happened in the same place that the original editor of the physics letters rejected the Higgs paper. So it's a nice little bit of coincidence there. Now, the Higgs particle is also known as the God particle. I'm sure if you've heard of it, you've seen that in a title somewhere. And Higgs was known to not appreciate this at all, as it just led to confusion. And the term the God particle is actually contributed to Leon Lederman, who said that his publisher suggested he call it that name instead of the original term that he used for it. Now, because of this discovery, among many other awards, Higgs was awarded the Nobel Prize in 2013 for physics, which he shared with Francois Englert, which was, quote, for the theoretical discovery of a mechanism that contributes to our understanding of the origin of mass of subatomic particles. Now, Higgs found out that he won from an old neighbor. He had gone for a walk to avoid any media attention, and he didn't have a cell phone, so he just found out from a neighbor telling him. Now, before this, he received many different awards and accolades. A notable one was a knighthood in 1999, which he actually turned down. He did later become a member of the Order of the Companions of Honor, but wasn't necessarily given the full story about what it involved and wasn't necessarily happy with that situation. He, however, did receive the order from the Queen in Edinburgh, and the title for this honor is actually CH, and he joked that he was, quote, an honorary Swiss. So Higgs did just die a few days ago, as of this recording, on a day in which many people in North America were celebrating this total eclipse. So he died in the month of eclipse, and coincidentally, he was born in the month of eclipse too, in May 1929. The eclipse happened 20 days after his birth. He was also an activist. He was very strongly against nuclear armament. However, he was part of some groups and left those groups once they start being against nuclear power. And so he was also an activist in his life and a very important figure within the city of Edinburgh, as well as the physics community. He didn't really like media attention, but it is well deserved for his work leading to these monumental discoveries. And his ideas have truly contributed to a new paradigm in physics involving these big experiments and monumental results in an effort to explain the universe. Two things I think we can learn from Peter Higgs, though, is that you don't need a eureka moment to make a big discovery. He worked hard at it. He went through the process, and it was still a big discovery that we know to this day, but it wasn't a eureka moment. And he also showed that rejection doesn't always mean the end of an idea. His paper was rejected by a very large journal. He made some changes, submitted it again, and it was accepted. And we are still discovering things related to it to this day. So rest in peace, Peter Higgs, and thank you for your contribution. Okay.
Jeez.
Yeah. So, with that, we'll end the episode. Thank you for joining us for episode 77 of the Hyperthesis, and bye, everyone.
Take care.
See ya.